All right, so I'm gonna be going back to 2.1. Uh, the only thing I covered in 2.1 was looking at the Cartesian plane, or most people just know it as the XY plane. There's the x-axis, y-axis. Remember, the origin is right where they cross. This was the first quadrant, second quadrant, first, second, third, fourth quadrant. And points that are on the y-axis are y-intercepts. Points that are on the x-axis are x-intercepts. And that was pretty much it that I wanted to do for 2.1, which then we jumped into graphing a linear equation, which we looked at the linear equation in slope-intercept form, the standard form, and then we graphed this linear equation. And we graphed it two different ways. One was using the table, and the other one was using sloped intercept form, which is right here, where we plotted the y-intercept and then we used the slope, the rise over run, to help us find another point. But I did say that using the table was going to be one of the most important ways you ever learn how to graph anything. So the rest of 2.1, I only covered the x and y plane from 2.1. The rest of it was looking at other types of equations. And we haven't seen the graph of these equations, but we saw the expression of these equations. And what I mean by that was we've talked about when things had an x squared on them. We looked at things that had x cubed on them. We talked about absolute value. We talked about radicals, and in particular, we looked at square roots. So these are all expressions that we've looked at. But technically, we can convert all of these to equations. This could be considered a quadratic equation, a cubic equation, we did look at absolute value equations, but with only one variable. Now we're going to look at them with two variables, and all of these we're going to look at them with two variables, and the extra variable is going to be our y. And the main thing is to be able to see what is the graph of these variables. So for these variables, for these equations. So I want to start with this one. So I want to start with y equals x squared. And I'm going to make a big graph just because I want everyone to be able to see how this is graphed. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So hopefully you're able to see this graph. Now, but to graph this, we can't use slope-intercept form. I can't just try to get a y-intercept because there is no y-intercept. So for this, we're going to have to use a table. And remember, the table is using this, the x and y table. And when we use this again, you can choose whichever values you want. If you want to choose your x's, you can. You want to choose your y's, you can. For starters, you can choose anything that you want. So let me see if I start with -2. So that means I'm going to replace my x with a -2, and hopefully I can find my corresponding y coordinate. That's the goal that I'm going for, to try to find my corresponding y coordinate. So to do that, I have to put, instead of putting x, I'm going to have the x being squared, and I have to replace it with the x that I'm using. So I'm going to replace that with -2. So I'm going to put -2 in there, hopefully you guys can see that. And then it's important to use parentheses because a lot of people forget this negative inside. And there's a huge difference between doing -2 squared and -2 in parentheses squared. Because this square is only being applied to a 2 and is not being applied to the negative. So this negative 2 squared gives you negative 4, where this negative 2 squared gives you positive 4. Because this 2 is being applied to the negative and the positive. I mean to the negative and the 2. So that's going to give us positive 4. So again, that means we have an ordered pair now. We can actually plot this. So negative 2 and 4. So if I start at the origin, that means I'm going to go 1, 2 places to the right. I mean to the left, because it's negative. I'm going to go up 1, 2, 3, up to 4. And that's going to be my first coordinate for this graph. Again, I'm going to have to do more if I want to be able to see this entire graph. Again, I can just as easily choose y coordinates. For example, let's say I want to use 1. And normally you can always just choose your x's. We are going to eventually look at logarithms, where logarithms is when I am going to want you to choose your x's. I mean, choose y's instead of x's. But again, this table you can choose with whichever ones you want. So to do that, I'm going, instead of plugging in this negative 2 in the x, I'm going to plug this 1 into the y. So that's going to look like this. I'm going to do it over here on the side just because it's going to look a lot different than just plugging in the negative 2. So if I plug in the 1 into y, so remember I'm plugging that into y now. So it's going to look like 1 equal to x squared. Now, in this scenario, they just made it a little more difficult, because before, plugging in negative 2, that just gives you negative 2 squared, gives you 4, and then you have what y is equal to. But to find your x, now this becomes a quadratic equation. And remember, as soon as you see an equation with a power greater than 1, you want to try to set this equal to 0. But when it's this scenario like this, where you have the x completely by itself and then a constant, I don't remember if we talked about this, but we can always apply the square root property here. Because remember, the square root simplifies the square. But don't forget, every time we do this, you want to make sure you add your plus or minus. So now this is getting a little trickier. So what that ends up being, we know the square root of 1 is 1. But now I have this plus or minus. So I have plus or minus 1 is equal to x. So that's saying when I use y, if I use positive 1 for y, I get 2 different x's. So that means I'm going to have one that has a positive 1 with it, and I'm going to have a 1 that has a negative. So that means I'm going to have a negative 1, and then there's another one that actually has a positive 1. So for this one y, I get 2 different x's. So that's kind of confusing. So in this scenario, it's best if we just choose x values. For example, let me choose 0. Now all I have to do is plug 0 into x, because once I square it, it's going to give me my y value. So 0 squared, that's just going to be 0. And done. That one's going to be right here at the origin. That's all I need. And then I do have these other ones that we found, but this was much quicker. I just had to plug into the x and I got my y. When I tried plugging into y, then it ended up doing all this extra stuff. So we're just going to choose x's. So we have 0, 0. We have this one here. We also have a 1 and negative 1. So I'm going to move, my x is negative 1, so I'm going to move 1 to the right and then 1 up here. And then I have a positive 1 for x and a positive 1 for y. So I'm going to move 1 to the right and then 1 up. If you had only used 2 points, you might have thought that this equation makes a line. But as you're seeing, it does not make a line. So I need to do a couple more points just because I want to make sure this isn't like a check mark. I want to be able to see, am I making a V? Is it a check mark? Is it making a triangle? I want to do a few more points to see what's happening. So I already used -2, -1, 0, 1. Let's try using +2. So again, I'm choosing X's instead of choosing Y's. So, and you would have seen this makes sense. Like, I know we used +1 for the Y and then did all this extra work. But if you notice, if you just plug in -1 into this X, well, -1 in parentheses squared gives you +1. And then 1 squared gives you +1 as well. So everything works out. Regardless if you would have chosen your X's, you would have got the same Y's. If you chose your Y's, you'll get the same X's. But choosing Y's makes things a little more complicated in this scenario. But here, I just have to plug in 2. 2 squared is equal to 4. So at +2, so I start at the origin, I go 1, 2 to the right, and I go up 1, 2, 3, 4. Now just to see a little bit more what's going on, let me try using 3 just to see what happens. So 3 squared gives me 9. So that's way bigger. So now at 1, 2, 3, I have to go up 9, which this goes 1, 2, 3, 4, 5, 6, 7, 8, 9 is all the way up here. So at X is 3, I'm going to go all the way up to 9. And just so we can see what's happening on this left-hand side, let's look at -3. So as you can see, this is not as straightforward as when we craft a linear equation when you need 2 points. That's why we need this table to be able to see what this graph does. Remember, when I plug in -3, I have to make sure I plug it in with the parentheses because the whole thing is going to be squared. And when you square the negative, it becomes positive. And when you square the 3, it's 9. So at -3, we're also going to go all the way up to 9. Now I can try to connect the dots of this graph. And let's see the shape that it makes. Again, it has to somehow curve back up. And maybe some of you are now recalling what this is. And hopefully that pops into your mind. This is a parabola. And that's the graph that the X squared makes. And we call it a quadratic equation. We also call it a parabola because that's the shape of the graph is a parabola. The equation is a quadratic, makes it X squared. And we're later going to see how we can sort of move this and graph around. But for now, we just want to be able to know what the graph of this equation looks like. Because we already saw what the graph of a linear equation looks like. The root word is line. Linear means it has a line in it, hence it makes lines. Now let's look at x cubed. The same thing. We're going to have to, we're going to look at when y is equal to x cubed. But same thing, we're going to have to use a x and y table. And here, let me make my graph for this one. Again, we'll do another big graph just so these are noticeable. I'm going to do 1, 2, 3, 4, 5, 6, 7, 8. Now I'll go as high as 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So, again, for same as before, if you can choose your y's and find the corresponding x, or you can choose your x's and find the corresponding y. But if I plug in my y, then I have an x cubed. Now I have an equation to the power of 3. Now it's going to involve a little more work to try to find the corresponding y. Or if I plug in negative 2, all I do is plug that into my x. And once that simplifies, there's nothing else I need to do to this y. I'll have exactly what y is equal to. So same thing, we're going to replace the variable with parentheses, and I'm going to input that negative 2 in here. So negative 2 is going to go in here. That leaves me. So again, now it's raising it to the third power. So that means it's going to be a negative times a negative times a negative, which is still going to give you a negative. And then if you do 2 cubed, 2 times 2 is 4, times 2 is 8. And when you're doing these graphs, again, maybe you're wondering, where am I finding these numbers? And you can choose any number that you want. If you look at the equation, as long as there's no issues with your equation, then you can plug any x that you want. And what I mean by if there's any issues, we're going to do an example next where this is the only one. I mean, there's the next equation we're going to look at. There is another one that involves restrictions with them. But we know that you can cube any number that you want. Any real number, at least. So you want to be able to use values that are to the left and the right of this y-axis, just because you want to get a rough picture of the graph. I don't want to choose numbers on the positive side. I don't want to just choose numbers on the really low side, because maybe I'm not getting the entire graph. So for example, if I only had picked numbers from 2 and above, this might resemble a line. We didn't know that, or maybe it might seem like it started coming and then it had to continue going down. Until we picked values on the other side, we noticed that this has to curve back up. So for this one, we have 2 and our corresponding y. So at negative 2, it goes up to 8. So I'm going to go up 2 to the right. So 1, 2. And then up 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's all the way up here. Oh, I made a mistake on this one, because what this is saying here, it's saying negative 2 times negative 2 times negative 2. And we know negative 2 times negative 2 is going to give us a positive 4. But when you multiply with this extra negative 2, it's going to leave you with negative 8. So the x, we still chose the correct x. So it's negative 2, which I'm going to move 2 to the left starting from the origin. But then I have to go all the way 1, 2, 3, 4, 5, 6, 7, 8 down. So I'm going to go all the way to the very bottom here. So again, we all make mistakes. So, just keep an eye on, make sure you're doing it correctly. But the reason how I knew I was doing it wrong is because I know what this graph is supposed to look like. And hopefully if we look over these enough, you'll know what this graph looks like. So you have to be able to remember these. When you see the cube, when you see a square, absolute value, you should already know what the graph is going to look like. But let's continue. Let me try using negative 1. So when I input negative 1 cubed, that's also going to leave me with negative 1. So from the origin, I'm going to move 1 left and 1 down. Now let me use 0. Again, I'm moving from left to right, choosing values. And then 0 to the power of anything is going to give you 0. So we have another value on the origin. And then at 1, when I plug in 1 cube, 1 times 1 times 1 is 1. And then if I use positive 2, I know 2 cubed gives me 8. Again, if you wanted to continue, again, you can always use more. If I use 3, that's going to be 3 cubed, which 3 cubed is 20. Oops. 27, which that would be all, it would continue above where you can't even see. So we're just going to stop at 2. So at 1, we got 1. Right? This ordered pair right here. That is literally saying 1, 1. x is positive 1 and y is positive 1. Now for the next one, I have to go to 2. So I'm going to go up 1, 2 to the right. And I have to go up 8. So again, just like before, it's important to pick both sides. If I would only pick from origin to the right, this might look like it's just going up, and we might believe it's just half of the parabola. But as we pick negative numbers, we notice that it ended up going below the x-axis. So this one has a look like this. It almost looks like it's going to be a parabola, but then it just comes right back down. So it makes this sort of S-looking shape. And that's for our Q. And our square is our parabola. And here we have these next two to look at. And since I was talking about this idea of restrictions, let's jump to the x squared one right now, so we can see what's so special about that one. So, for example, same thing as before. I'm going to put y equals square root of x. And I'm going to use a table again. And here's my graph. And don't forget, when we're making this graph, this graph is using only real numbers. The reason why I bring that up is because remember when we looked at square roots, when you put a negative inside the square root, you get an imaginary number. But we can't put imaginary numbers on a real number line. So you want to be careful with that. Sometimes we get so stuck into like doing things routinely that we don't stop to think about the concept that you're working on. So what I mean by that is because we know that if I were to put negative numbers into this x, I'm only going to get imaginary numbers out. But the only thing I can put on this x and y graph is real numbers. So that means I have to choose x values that are going to give me real numbers. And again, you can choose any number as long as it gives you a real number. It's fine. But at the same time, when we're simplifying square roots, we have to remember what the index is asking us for. Remember, the index is that number inside that little wedge. When you don't see that number, you automatically assume that number in that wedge is a 2. And what that 2 does is asking the radicand for two numbers that are identical to each other, two factors that are identical and multiplying. So that makes it tricky. I can't just, in the last previous problems, I can't use -1, -2 because it's not that the x value can be negative, is that the radicand. What I mean by the radicand is anything under the radical, because this could say x plus 1. Anything under the radical cannot be negative. So x plus 1, x could be a -1, because -1 plus 1 is 0, and that's a perfectly good way to simplify a square root. It's like the smallest square root. So you want to be thoughtful of the values that you're choosing. I can't just choose any negatives. I can choose 0 because I know the square root of 0 is just 0. And I already know I'm not going to choose any of these values. So I already know for sure the graph is not going to exist on this side because I can't actually input negative numbers and expect real numbers out. I would end up with complex numbers. Now let's continue. We can use 1. What's the square root of 1? Well, that's not too bad. That's 1. Let's plot our first one. It was at the origin. Our second one is 1, 1. And now, this is where you want to be careful because then some people might just jump. Let's just do 2. And 2 is perfectly good number. There's nothing wrong. Square root of 2 is an irrational number, but it's still a real number nonetheless. The ones we can't be using is imaginary numbers. And we know when you have a negative under the square root, you end up with imaginary numbers. So the issue with choosing the square root of 2 is just we don't know the exact value of it. All we can do is give a rough approximation of it. So the square root 2 is approximately 1 point, and by approximately, I'm going to use these squiggle lines to, this isn't exactly that, but this is approximately 1.4. And now to graph this, that means you'd have to go over 2 units to the right because your x value is 2. But then you have to move up 1.4, which is almost 1.5. And I'll say that's about here. But there's values that we could use that we do know how to find the square root. It's not that 2 doesn't work. It's not that 3 doesn't work. We just don't get nice numbers. So when it comes to trying to graph it, you might get confused with these decimals. So we already know 0 simplifies nicely, and that's actually the smallest square root possible. There's nothing else you can input that's smaller than 0. You could put anything bigger than that. We saw 2 works, but the problem with plugging in 2, we don't know the exact square root. As if I plugged in 4, I know the square root of 4 is 2. So if I go over 4 to the right, 1, 2, 3, 4, and I'm going to go up 2. And these are a little bit nicer. Again, there's nothing wrong with the square root of 3, there's nothing wrong with the square root of 4, 5, 6, but the problem is we don't know the exact value of those. When we do a square root of 5, we're left with some decimal that's going to make it difficult to graph. So when you're using these, you want to be thoughtful about, it's not about what x can be, because this could have easily be an x plus 1, and then some other problems wouldn't work. Or, for example, if this was x plus 1, you could use -1, and -1 would be a perfectly good answer, because -1 plus 1 is 0, and the square root of 0 is okay. So it's not that x can't be negative, it's that anything inside the square root cannot be negative. It has nothing to do with specifically it doesn't have to do with specifically with x. It's about the radicand. Anything under the radical cannot be negative. And then again, we know what 9 is. The square root of 9 is 3. 1 iterate one more time. There's nothing wrong with the square root of 6. There's nothing wrong with the square root of 7, square root of 8. The problem is they're not going to give you nice numbers. Since we know how to work with square roots, this is what I mean. We can choose numbers that work nicely. So for instance, 4, I'm going to move 1, 2, 3, 4 to the right. I already got 2. And then I can't necessarily, even though 5 is the very next one, the problem is I don't know what the square root of 5 is unless you want to put it on a calculator and try to put it on this graph. It's perfectly fine. And we do go up to 3, but that's all the way up until 9. So that's 1, 2, or let me put an extra piece. So maybe just so we can see what happens as you go further out. So let's say we extended this. So that's 1, 2, 3, 4, 5, 6. I'm going to extend this line. 6, 7, 8, 9. So it's not until 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you go up 3. So it's going to be right around here. Again, there's nothing else that can go here. 0 is the smallest. And then this is the graph of a square root. It's starting from the origin and then it's slightly increasing slowly forever. It doesn't go straight horizontal or vertical. It doesn't just shoot up like an exponential. It continues on this curve and it gradually goes up. If you see here, it went up 1, but then slowly it went up a half after that, and then it's only adding a half after that, and then going up very little increments. So it might almost look like it's a straight line, but it does go up ever so slightly. But that's the graph of a square root. one of the first functions you need to start thinking about, because it actually has restrictions to it. And the thing is, this is a real number line. So you can only put real numbers on a real number line. And lastly, we looked at absolute value equations. Now let's look at what the absolute value inequality looks like. Absolute value equation, I mean. So we have x squared, y equals absolute value of x, sorry. Same thing, I'm going to use a table to help me graph this. Let me put my graph here on the side. Whoops, I don't know why I keep going like crooked for some reason. I don't know why I can't just go on a straight line. But here we go. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And one more. 1, 2, 3, 4. So, same as before. I can choose x's, but let's remember, don't just jump straight into the problem like a robot. Let's think about this. What did we say absolute value meant? Absolute value meant the distance away from 0. So that means anything that comes out of the absolute value is going to be positive. And that's the only thing that we did with absolute value. There's nothing there's no restrictions on it. There's no special numbers you can't use. You can plug anything you want into that absolute value. Again, I'm randomly choosing numbers. If I do the absolute value of -3, again, everything that comes out is just positive. So if I go 3 places to the right, then my y have to go up 3 places up. So it's right here. I can use -2, same thing. Absolute value of -2, it just converts it to a positive. So at -2, we have 2. If I use -1, the absolute value of -1 is just 1. So it's here. If I plug in 0, the absolute value of 0 is 0. So we have 1 at the origin. That's the thing. If I try making a graph now, it's going to look funny. So it's better that we use more points. So hopefully you saw a slight mistake that I made, because this ordered pair is supposed to be from -3 to positive -3 for your x, but +3 for your y. So if we move to the right 3, we have to go up 3, which is going to be right here. I accidentally went 1, 2, 3, 4, and that one stayed up. Instead of 1, 2, 3, up, then 1, 2, 3, 4. So we get to see a better idea of this. If I use 1, oops, sorry about that. The absolute value of 1 is still 1. Absolute value of 2 is still 2. So, again, oops, not parentheses, absolute value. We know that absolute value just converts everything into a positive. So at 2, we have, so at 1, we have 1. At 2, we have 2. And so on and so forth. But this is going up by 1, right 1, up 1, right 1. So all these ordered pairs are at 1, 1, 2, 2. There'll be another one at 3, 3, 4, 4, 5, 5, 6, and so on and so forth. And on this side, it's just going to have the negative ones, but we know that everything that comes out positive. So this ends up making a nice, perfect V shape. That's the graph of the absolute value. Now, I don't expect you guys to always be doing all these tedious work with these tables, but I want you to be able to memorize these graphs. Absolute value, square root x cubed, and last but not least, parabola. So you want to make sure you know these. Whenever you see a square, start thinking parabola. Whenever you see a cube, start thinking this S shape. Whenever you start thinking square root, don't forget, when you're choosing your values, make sure you choose them wisely. Because the smallest number that you can take the square root of is 0. And then only 1, 4, 9, 16, 25. It's only a few more. So don't forget when you're graphing it, or at least try to remember what the graph looks like. And then the absolute value makes a V shape. So try to remember that as well. And then just for the sake of showing it again, just so hopefully you remember. So just quickly, I have 1, 2, 3, 4, 5. So the first things we looked at were linear equations. Now we've seen parabolas. We've seen x cubed. We've seen square root. And we've seen absolute value. And technically we've looked at fractions as well, when the denominator's in the fraction. But I don't want to do that just yet. Or actually, I don't think we've seen that type of equation. I want to get to that a little later. But linear, quadratic, cubic, square root, absolute value. So you have to be able to know these ingrained in your head. They have to be able to be ingrained there forever. You see an x cubed, you already know it's that shape. You see an x squared, you already know it's that parabola. See a square root, you know this shape, and you know. And if you see the absolute value of x, you get a v. Exactly. So that's going to become important to be able to see the graph for a couple reasons. In the next couple sections, we're going to talk about sort of moving this graph around. And then being able to further identify these graphs. So first, when we first started the class, we weren't looking at equations. We were looking at expressions. We factored x squareds, x cubes. We simplified absolute values. We even did some small absolute value equations and inequalities. And we looked at simplifying square roots. So before it was just an expression, but now we are able to rewrite all of these into an equation. Now, the question is, can we describe them even further? And yes, the answer is yes to that question. We're going to look these into more depth, and what we're going to do is talk about this idea called functions. If you took this class already, you know what that is. But if you haven't, we're going to talk about that in our next video. So this would be jumping to 2.3. And the idea is being able to see if any of these equations are considered functions. And what's the definition of a function? And where does that come from? So just keep these in mind. Don't forget linear, quadratic, cubic, square root, and absolute value. You have to have these memorized. So definitely for homework, I'm not going to give any homework on these for 2.1. Just go over these. Try